Good morning, good afternoon, good evening. Welcome all to our next episode of the Yugabyte Friday Tech Talks. I'm Kannan, one of the co-founders at Yugabyte, and it's my pleasure to welcome today Suranjan Kumar, who's one of the directors of engineering. And Suranjan, welcome. And why don't you introduce yourself? Just maybe tell us briefly kind of things you work on at Yugabyte, and also then go ahead and introduce the topic for today's talk.
Sure. Thanks, Kannan. Thanks, Kannan, for introducing. Hi, all. I am Suranjan Kumar. I have been working in data domain for last 15 years. And in the Yugabyte, I have been for the last 1.5 years. And I have been working on mostly in CDC and on the database side and in the ecosystem side, creating different kinds of connectors. And today I'll be talking about the change data capture, its implementation in YugabyteDB, its design and architecture, and provided a demo on that. Yeah.
Great. I think you can go ahead and share your slides.
Sure. Yeah. So in today's session, just to give you an idea about the whole session, what I'll be talking about. First, I'll just discuss what is change data capture and what are the motivations around this and the kind of use cases that we wanted to solve in YugabyteDB. Then we will talk about the design choices we considered and some rationales behind those. And as this is a talk by an engineer and for engineers, I'll go into the details of design and architecture as it is implemented in YugabyteDB. And then in the end, I'll just give a brief, very short demo and just introduce some user touch points and show how it is easy to use CDC in the YugabyteDB. So what is CDC? I'm not sure I need to introduce it, but just for the in the brief, right? It's just a process of identifying, tracking the change in the database, right? And almost all of the database have it. However, there are no standards, and that is why the choices that we make, the kind of APIs that it has, plays a very important role in how it is being used by the customers. And in my opinion, the goal of CDC is to liberate your data. I mean, it should be such that any data systems, and we know that there are tons of data systems, everybody is trying to solve different kinds of use cases. They should be able to take advantage of data when it is presented to them. There are different kinds of use cases in terms of microservices. There will be different microservices, each one of them listening to each other, listening to the changes from one microservices to another. We also may want to just replicate the data across different data storage, whether it is a cloud object storage or whether it's completely different database like MySQL, or something like very specific data systems like Elasticsearch, where you just go and do a text search, which is made for text search indexing, right? Different applications, for example, auditing and compliance, right? They can take advantage of CDC. They can listen to changes. They can take immediate actions if the changes are affecting any kind of auditing or compliance issue. So once we know the very basics of CDC and its use cases, let's discuss the kind of requirement that we considered inside YugabyteDB that we wanted to solve for our users. The requirement that we considered were aligning with the YugabyteDB core values. It was like resilient to failures. It should be horizontally scalable, as YugabyteDB database itself is. So as and when YugabyteDB clusters horizontally scales, the CDC solution should also scale. And similarly, just as YugabyteDB cluster handles node failures, the CDC solution should also be able to handle the node failures. And transparently, you should not worry about these kind of issues at all. We also wanted to support variety of use cases, for example, analytics being one of them. However, we know that these days microservice architectures, they are very popular. And we also wanted to support these kind of architectures where it will be easy for one application to listen to another application, changes made by another application. Being an open source, we did not want to limit ourselves to particular data formats, which will be specific to Yugabyte. And one of the reasons we went for open data exchange formats like JSON, Avro, Protobuf, so that all kind of data systems can take advantage of it. Similarly, we do know that there will be multiple applications listening to the changes. There are different kinds of applications, different kinds of data systems. They would want to listen to change on their own way, on their own frequency. And for that, we do not want to limit ourselves to like single consumer or single subscriber. And at the last, this schema evolution, we know that not everybody supports schema evolution, but we know that data model changes over time. And it makes life of application developer a bit difficult. There are certain downtimes because of these kind of changes. But we wanted to support it to make the life easier for app developers so that they can take advantage of automatic schema evolution support from CDC. One of the requirement which one of the core of Yugabyte is like compatibility with Postgres. So we wanted to be as close to Postgres as possible in terms of data type mapping as well as the API. So once we know the requirements, the design choices that we considered and the options we chose became a bit easier, but we wanted to explore that and just discuss it so that all the users of CDC, they will know why we made those kind of choices. So the first choice is how do we capture the change data, right? And there are popular ways, for example, triggers, many CDC solutions use query, and many CDC solutions obviously use log reader also. We understand that all the applications that use YugabyteDB, they are latency sensitive. We did not want to impact any of the read or write workloads. And one of the reasons we chose log reader was to isolate the read and write workloads from the workload of CDC client. And that way we could separate the resource usage of CDC service, and that we will discuss as one of the components that runs in YugabyteDB cluster. CDC delivery, we wanted it to be a synchronous micro batch rather than synchronous transactional or an aggregated where it could be large batches. We understand there are advantages to that. However, we wanted to give an option to users where you can increase the batch sizes and try to solve your use cases accordingly, rather than fitting into one of the transactional or aggregated batch use cases.
And Suranjan, it's probably worth clarifying that the advantage of the micro batch approach is it keeps the CDC lag or the delay like almost near real time, without like really compromising on performance. Like if you do row at a time, then it's like, too much load. So micro batch is kind of a right middle point where you still get the benefits of some batching, but keep the delay very small and it's near real time.
Yeah, certainly. So and that is configurable. So that is up to the user's configuration as well, that how much of lag they are comfortable with, and they can increase the size of the batch or they can decrease the size of the batch and polling intervals to get the kind of lag they will be comfortable with. Ordering guarantees. I mean, everybody would love to have total order. However, we know that there are costs associated with it. Also, we understand that there are applications that use distributed databases like YugabyteDB. They do design their applications taking sharding into the picture and taking advantage of the sharding in distributed databases. And to that end, we decided to support per tablet ordering so that the applications that are designed for these kind of databases, they can get the changes in order if they are made in the same shard. So it's in between, midway from key level ordering to total ordering, where even if there are multiple keys, the changes are made, but if they are in the same shard, you get the changes in the same order. Similarly, for the delivery semantics, because we developed the components like client as well as the server, we made sure that unless and until there are any kind of failures and drastic failures, for example, the whole of YugabyteDB cluster goes down or whole of the client cluster goes down, in those cases, if we do not get those kind of cases, the delivery semantics will be exactly once. However, in the failures where the complete cluster goes away, in those cases, the delivery semantics is at least once. That is also for the batch, the last batch that we delivered. Consistency guarantees, similar to ordering guarantees, it is at the shard level. It is timeline consistent. All the changes that goes to a shard, which we call tablet in YugabyteDB, it will be timeline consistent. That means all the changes that comes in the order that they were made in the shard, it will be exactly that order it will be delivered to the client. CDC formatter we already talked about in the requirement that we wanted to be as open as possible. We wanted to support all the open exchange format and data exchange format. Here we deviated from Postgres of PG output, for example, but the reason we chose JSON and Avro was because we saw that even PG output finally was being converted to one of the formats like JSON and Avro. Initial snapshot, we do realize that there are, it's difficult if you look at some of the solutions, they provide some kind of query-based initial snapshot. However, we provided the same APIs for initial snapshot so that user does not need to tie their solutions to get the snapshot of data and the changes. The snapshot means that the data that is already present in the table, that we should get first, and the rest of the changes, then the future changes that are made, that will get streamed.
And maybe, Suranjan, you could clarify, is the initial snapshot done automatically, but kind of using a query mechanism? Because for that path, we can't use the transaction log reader that we described in the first line. So is the initial snapshot done more from reading, say, backup restore kind of flow, or it's actually reading the data with a query style?
Yeah, it is read through an iterator. It's read from the table. However, the beauty is that user does not need to worry about it. So the CDC client itself takes care of it. If we look at it to some of the other databases, user has to worry about how to get the snapshot and then get the data from the disk.
And that snapshot mechanism is also parallel if you there are some tasks. Yeah, thank you.
So we'll discuss how do we scale in that and because the snapshot is exactly transparent to user does not even know how the snapshot or the changes are coming to the client. So it is completely transparent to them. For schema discovery and evolution, we support historical discovery of schema. That means in the past, we read the schema and we decode the data according to the past schema. And it helps to the end user in the sense that they do not need to track the changes. Retention, it is time-based, disk size-based. If you understand that applications might not be always available. Not every product is as stable as YugabyteDB in terms of resiliency. But in case they are away for some time, we can still store the changes in the wall, and we'll make sure that when the client comes back, the changes are delivered to them. Yeah, so with the requirements and design choices covered, I would like to now go a bit deeper into what is the architecture and the design of CDC in YugabyteDB. So there are mainly three components. One is like CDC administration and metadata management. The second is CDC service, and third is CDC client and the connectors that we talk about. So in this diagram, what we see is CDC administration and metadata management, which is identical to what we do in YugabyteDB for other administration and metadata management. There is a YB master process, which is itself a replicated process. Once the kind of APIs, administrative APIs like creation of a stream or listing a stream, they directly connect to YV master. YV master on creation of stream manages the metadata, which are replicated to multiple nodes, so that even if a node goes down, these kind of metadata are available, as well as the service. Then the CDC service part that runs on each of the T server. This is a stateless service that runs on each of the T servers, and it scales as the T server scales. I'll talk about a bit deeper about CDC service in next, further slides. And then the CDC client and connector. The client CDC connector is based on a popular framework called Debigium, which is itself based on something called Kafka Connect, which most of the folks must be familiar with. We have written a connector based on that, and that pulls the data from YugabyteDB and ingests it into Kafka. Yeah, so let's go a bit deeper into CDC service. As I said, CDC service runs into each of the T server. The job of CDC service is to get the request from CDC client and serve the data from disk or some of the internal data structure, as I will explain. So on receiving the this get change request, which has some of the metadata with regards to what kind of data it wants, for example, the table ID or the tablet ID and the offsets. Depending on that, it finds out the source from where it needs to pull the data, and it contacts a component called CDC producer. The CDC producer will read the wall of the corresponding tablet. Wall might have lots of entries. It needs to filter the records which are relevant. Some of the records will have the data with it. Some of the records will have, in case of distributed transaction, will have the transaction ID associated with it. And depending on the kind of records, it will either populate its batch or it will contact an internal data structure called IntentDB, which stores all the changes for a transaction. Right. So for with a transaction ID, it will fetch the changes if required. It is not necessarily for each of the records it is required. It will fetch those changes, populate in its batch, and then it connects to a decoder. As we know, each of the column can have different types. We store this information in TG catalog. We load this, cache this catalog information in T server. We get the data types of each the column and decode this binary data into a format that can be understandable by the client. After the decoding, this is a kind of optimization where we try to update the checkpoint. The checkpointing works in a way that we piggyback some of the offset information, and when we know that client has processed some of the offset, we asynchronously checkpoint the information in a table called CDC state. The CDC state table is like any of the user tables. However, it's a system table, but all the guarantees of consistency, availability, etc., will be similar to what any of the user table gets. This is also distributed across the YugabyteDB clusters. So on checkpointing the offsets, we return the response to the client with the batch of decoded records. Yeah, so once we know the internals of CDC service, now let's try to understand from the user perspective that, okay, how does the whole CDC pipeline works? So in this pipeline, if you see the CDC service is running YugabyteDB. Our connector, the YugabyteDB connector, which runs in Kafka Connect, which will pull the data from CDC service by talking to CDC service from YugabyteDB and ingest it into Kafka. Once the data is in Kafka, Kafka has its own rich ecosystem of connectors that can pull the data from Kafka and ingest it into different data systems or storage. The advantage that this model provides is that first of all, we are compatible with Postgres. We map all of our data types that is present in YugabyteDB to similar data types that Postgres maps to. And so that all the applications that currently runs using Postgres CDC will also run for Yugabyte CDC. Now let's also go a bit deeper into how does this YugabyteDB, how does this YugabyteDB and the connector interact with each other and provide the core values of resiliency and the horizontal scalability, right? So if you look at this diagram, this YugabyteDB cluster can itself have multiple T servers, and these tablets will be again distributed across T servers. The second cluster is the Kafka Connect cluster. It can again have multiple worker nodes, and these tasks of our connector can be across different worker nodes. The tasks distributes which all tablets to pull. The total number of tablets are distributed across tasks. So what does it mean? That the task can be on multiple machines, the processing is distributed. The data that we are fetching from YugabyteDB cluster, that can also be on different machines. The processing of the CDC service is distributed on the YugabyteDB side. And then when we fetch and put it into Kafka, the Kafka cluster itself is a distributed cluster, and these topics can again reside on different machines. So in the whole pipeline, all of the components are a distributed product. All of them take care of resiliency and horizontal scalability. So as YugabyteDB cluster scales, we can scale the Kafka Connect cluster to take advantage of scalability and fetch the data for at the higher load. Similarly, if there is a need to scale the Kafka cluster, we can do that as well. Yeah. So with this architecture, I would like to now explain a bit about the administration API, and then I'll also show a small demo. So the administration API is very simple. Just create a change data stream on a namespace, which is nothing but a database. The YBadmin is a tool that connects to YugabyteDB cluster, and by taking a namespace, it creates a change data. It creates a stream, and it provides us a stream ID to the user. This stream ID binds all the tables that are present in the database to the CDC stream. Now, any other APIs, for example, for example, get change data stream or delete change data stream, has to operate on this DB stream ID. The same DB stream ID can also is also used by the client, as I will show in the next slide. So these are the usual administration API. You can delete a stream, you can list to see multiple streams if you have created. You can get the information about the stream, which all tables are part of it. This is the connector configuration that user has to submit to the Kafka Connect cluster. So we have written our own connector, which is called YugabyteDB connector. The config it takes is simple host name, where the YSQL endpoint runs. Then the master addresses that it connects to some metadata informations. The stream ID that I was talking about. So when you create a stream ID, you get a when you create a stream, you get an ID of that particular stream that you can feed it here. And then these are like authentication information for the user that wants to connect. The table include list. So our database can have like multiple tables. However, we understand that the application might not be interested in all the tables. So this include list specifies what all tables the application is interested in. So if hundreds of tables, if you are interested in just 2 tables, you can just provide 2 tables in the list. This list also contains, it can also it can also basically pattern match with the schema name or table names to get all the schema rather than typing all the table names. Yeah, so with this user touching changes, I try to show a demo. In the demo, what I would like to show is that user making some changes to a table in the YugabyteDB. The DBGEM connector of YugabyteDB will fetch the changes from this table, push it to Kafka. There will be two applications. One is the web UI, which directly connects to Kafka and gets the changes. Another is sync connector that is deployed to Kafka Connect, and that pulls the data from Kafka and publishes it to Postgres. So I'll just share my screen. Okay. Is my screen visible? I'll just
Yes, Suranjan.
Okay. Yeah. Yeah. So I have been running the setup on my local machine where you can see the Postgres is running, the Kafka UI is running. I have deployed the Kafka Connect cluster. Then I will run our connector inside it, and then I will make some changes to the tables and so that that data is replicated to Postgres and the UI. Yeah, so if you see this is just a simple call command which takes that the config that I mentioned. In this case, the table include list contains YFTT underscore test. And yeah, and we need to provide the DB stream ID. So first, I'll just create a stream ID. So using the YBadmin command, I just created this stream ID. I got a stream ID. I'll just fetch it and put it into the config. Yeah, so I have fed this stream ID to this config, and this is the table include list. Once the connector is deployed, it starts listening to the, it connects to the database, and then it starts listening to the changes. Here I have two cells. One is connected to YugabyteDB cluster, another is connected to the Postgres. In the YugabyteDB, if I see, there is a table called YFTT test. Currently, there is so currently there are no entries. Similarly, in Postgres, if we see,
I guess there was a row from a previous run.
yeah,
All good.
Yeah, so in this case, we see that both the tables don't have any entries, and then I'll try to insert something, and I'll expect that this reaches the Postgres. Yeah. And I'll do another operations. For example, I'll just update it. Then I'll just delete it. So this is completely zero code setup, right? Your application is just connected to YugabyteDB, all the operations that you are doing in YugabyteDB, and you are keeping, you are basically taking the data in completely different data systems. And while YugabyteDB is taking care of all the consistency, availability guarantees, and making sure that the same changes by the same applications reaches to another database. I'll also show another application that
we're a little bit over time, but maybe that's okay. I think we can probably go for 5 more minutes.
Okay, just. Okay, so this is the second application that I just wanted to show. So these are the changes that comes as and when we make changes to the table. This is the you can consider this as a second application which is listening to Kafka topics and processing the data. This could be anything. For example, this is a web UI, but this could be another microservice application.
So, Suranjan, is what you're showing showing the one-to-many capability? Like, do we support multiple subscribers to the same tables?
Not multiple subscribers. In this case, the single subscriber itself, because Kafka took care of that. However, if you do not want to have if you want to have data in different topics, which could be use cases and which is recommended use case in some cases. For example, you want to take a snapshot. You do not want to disturb your existing topics in that case, right?
Got it.
So
okay, so what you were showing was the multi-level subscription was happening from the Kafka layer right now.
Yeah.
And can you clarify what, like in change data capture? I believe today we give you the after image of the change, but there are like, I covering that somewhere, or if you could talk to some of the flavors and potential things we could do in the future.
Yeah. I was going to talk about that. Let me check. So is my screen visible? My slides?
Yeah.
Okay. Yeah, so in the future work, people in fact have shown really great interest in this CDC service, and they want their life to be much easier. So they in fact want us to manage the CDC clusters, right? So one of the feature that we are coming up with is a managed service itself, where you don't even need to manage the connector. We will be running it inside our process. For you have to just provide the sync. So we'll be supporting Kafka cluster, for example, Confluent Cloud or S3. You have to just provide me the authentication details and the URL of the sync. Another is, as you mentioned, the before image of a row that has been some of the users has asked for that, and we are working on it. Where the before image, while we are sending currently only that after image of a change, we at the same time in the same record we'll be also populating the before image as well. So that is under works.
And one related question, Suranjan, if a table has say 100 columns, is it possible to say I only want the after image for these 10 columns?
Currently not. However, you can achieve it, for example, at the Kafka level and connector level. So at the from our connector, yes, it is possible.
Okay.
Although we fetch all the columns from, user need not worry about it. We might fetch all the columns from the YugabyteDB. However, user in its sync will get only particular column.
So it's a later stage filter, but presumably we can take that information and push it down so that we fetch only the minimal thing from Yugabyte. Okay.
Yeah, that would be a good optimization.
Yeah.
I also wanted to show some real world use cases that we have seen, and it's really interesting. So one of the use case has been that a customer wants because they are shifting from MySQL, they want to keep still some of the MySQL instances alive and sync all the changes that come to YugabyteDB to MySQL. It's a huge cluster. It's a 100+ tables. It's a 25 node cluster across 3 regions and replication factor of 5. The initial snapshot that is there, which is like 1 billion rows, and there are around 10K rows per second of changes that are coming. So, and to just think about this, that you do not need to write a single line of code to keep this data in sync in your MySQL. It's a great help for the application users. Otherwise, they would need to write to 2 different systems, making sure that they are consistent. Similarly, for another customers, again, this is like trade data where around 200 million plus rows is supposed to be synced between different data systems like Elasticsearch from YugabyteDB. So these are definitely some kind of learning experience for us. With this experience and the kind of future features that we are planning, we are looking forward for more suggestions from users who use PC and provide us with feedback as well. Yeah, that's it. I guess these are references. If anybody is interested in to go deep dive into this, they can read about this, and definitely they can come to us on the Slack or from the OSS side, or come to our channel, YFTT channel, and just ping us, and we will be happy to connect and explain. And obviously, love to hear feedback.
Thank you so much, Suranjan, for a wonderful talk, and also for your work in this this area. Very fascinating and important part of Yugabyte's DB's offering. And thank you everyone for joining. Join us next week for a talk on transaction isolation levels in YugabyteDB. And over to you, Suranjan, for final comments.
Yeah, thanks a lot, Kannan. Thanks to everyone who has joined, and I would love to hear. Please come to join us on Slack, and if you have any questions, you can just shoot, and we'll be happy to answer. Thank you.
Have a wonderful day and weekend, everyone. Bye.
Bye, everyone.